Big news for the study of the sense of smell. Recently, for the first time ever, the molecular structure of a human olfactory receptor has been directly observed. A team of scientists used an electron microscope to image it in its active state, bound to an agonist ligand and to a G protein complex. This is huge. This is one of the proteins in the nose that detects smells, 51E2 to be precise, and we previously identified it as a receptor for an acetic or vinegar-like note, based on its sensitivity to acetic and propionic acids and ionone. This 3D model is a piece of information that shows how one specific protein responds to one specific aroma compound, but other compounds that activate 51E2 probably also work via the same principle. Also, other receptor proteins probably work by an analogous mechanism, since their structures are predicted to be very similar. So, what does this mean for decoding the perception of smells? Well, it makes it possible to predict at least some receptor responses to odors, meaning more information about each receptor, allowing us to make better guesses about which note or notes the receptor's neurons contribute to odors. Importantly, the paper also demonstrates why larger organic acid molecules are not agonists for this receptor, since they can't physically fit in the binding pocket. We've run some simulations on a closely related receptor, 51E1, and we found that its agonists, which have longer carbon chains, can fit into its pocket because of a more flexible and less bulky side chain in one of the key places identified in the study. So, we are working on being able to predict the activity of organic acids on the 51E subfamily of olfactory receptors, and then we will expand to other receptors and see what predictions we can make there. Now, one puzzling thing about this new experimental result is that it doesn't predict why ionone activates 51E2. The molecule simply can't fit into the binding pocket. It's not known whether ionone activates 51E1, but another compound, delta-decalactone, has been shown to activate 51E2 moderately and 51E1 slightly. Here, too, the molecule is too big to fit. So that could mean that a second binding pocket exists somewhere in the protein, and it's a matter of finding it and running primary doc to determine how the aroma molecule is most likely settling in and what molecular features and interactions lead to activating the protein. So that's the present state of things as far as the current direction of primary odors and current development on primary doc. Thank you for watching.